Hey, how's it going everyone? Welcome to the next video. This week we're going to have a look at chapter 12, which is on rates of change. So a rate of change measures the change in one variable relative to another. An oil spill may grow at a rate of 20 square meters per day. The number of subscribers to a newspaper may decrease at a rate of 50 people per month. So practical situations, the rate of change is often expressed with respect to time. So most of the time we're going to be dealing with t, little t for time. Gradients as rate of change. So we've had a look at linear functions. So a straight line graph whose gradient or slope, and it's not very clearly written there, but we can calculate gradient or slope by m equals our second point, take our first point over the x to take x1. So that's to calculate the gradient. And we're going to be using that formula in our examples. So this gradient measures the rate at which the y values change with respect to the change in the x values. So the gradient actually measures the rate of change for the function. The rate of change of a linear function is a constant, so either the function increases, so if m is greater than 0, or it decreases steadily if m is less than 0. If we come up to the situation where we have m is equal to 0, the function neither increases or decreases. And we'll have a look at that in examples later on. So the rate of change of any function is measured by the gradient or slope of its graph. However, we can get nonlinear functions. It depends on what point of the graph or what instant it is to be measured. So we've got three different situations here. The linear function increases steadily as x increases. So we've got a straight line, it increases as x increases. The linear function decreases steadily as x increases. So as we go along the x's, our y values are going to decrease. And the last one, this nonlinear function decreases as x increases. So we're decreasing, but as x increases, but not at a steady rate. So see the difference between the straight line and the nonlinear function. So this one steadily decreases, this one decreases in a not steady way. We know how to find the gradient of a linear function, and learning how to measure the gradient of a non-linear function is what we're going to be doing in this chapter. The average rate of change. So we've got the example, a car journey of 240 k's completed in 4 hours may not have been undertaken with a steady driving speed of 60 k's per hour. The speed of 60 k's per hour is an average speed for the journey found from the calculation. If you remember from physics, the average speed equals the distance traveled divided by the time taken. Speed equals distance over time. So it gives an average rate of change for the distance with respect to time. However, this might be what the actual distance traveled by the car over the 4 hours. So between the first hour, we can see that it increases non-linearly. So we're slowly increasing our distance. So we're going fairly slow to start off with, and then we speed up as we get towards the first hour. After that, from 1, 2, we steadily increase, so we maintain our speed over that period of time. When we get to B, we don't travel anywhere, so we've probably stopped, so having a short rest. After the third hour, again, we slowly increase our speed with time. So that's a possible scenario for the journey. So our average speed, as we had a look at In this one here, speed equals distance over time. The average speed would be 60 k's an hour, and that's by calculating 250 divided by our 4 hours, which gives us that straight line in there. So the aim of this chapter is to look at the individual parts and have a look at the gradient of those, the rate of change between a particular time. So, as I said, the average speed of the journey is a gradient of the line joining the origin and the final destination. So for any function y equals f of x, the average rate of change of the function over the interval a to b is calculated as followed. We have f of b, take f of a divided by b, take a. So that just comes from our y2 take y1 over x2 to take x1. We're just putting it into terms of our function. So f of b would calculate that y2 part. So if b was 4 for this example, whatever our function is, 4 would go into it, would get some answer, which would be 240. So 240, take our initial point at 0, so 240 take 0 would be 240 divided by 4 take 0, which is 4. So that's where that comes from. So this is the gradient of the line joining the endpoints of the interval. So looking at an example, we've got a water tank containing 1,000 litres of water. The volume decreases steadily, and after 4 weeks there are 900 litres of water remaining. Show this information on a diagram and calculate the rate at which the volume is changing with respect to time. So we're going to have capital V, meaning our volume in litres. And we have our time, little t. And I'm going to say V naught, so our initial volume, we said we started as 1,000 litres. So we'll have a little subscript 0, meaning our initial point. I'm going to say after four weeks, so V of 4, we had 900 litres of water. So we've got the two endpoints. So that's when t equals 0, and this is when t equals 4. So we have these initial positions, 0, 1,000, and we have 4, 900. So to calculate the, actually we'll draw our graph to start with. So our initial position was at 0, 1,000, and we end up at 4 and 900. So if we connect those two dots, it's decreasing at a steady rate over that time. This is T, this is volume. So the rate of change of the volume is going to be the gradient of the graph. And to calculate the gradient of the graph, we have the change in volume over the change in time. And instead of writing change in every time and change in time, we usually note it as this little triangle. So change in volume over the change in time. Just makes it easier for us. So if you see that little triangle, means change in. So our change in volume is going to be our 1000 take 900, which is 100, over our change in time, which was 4 take 0, which is 4, so we get 25. Except I need to swap those around, so it should be our final point take initial. So it's always, actually I'll write that in. That's so change in, meaning always it's our final take initial. So if you see that little symbol, it's always change in, meaning final position take initial. So that was our final take initial, so it should be just the other way around for that. So it should be 900, which was our final position, take 100, which is minus 25. So the volume of water is decreasing at a steady rate of 25 litres per week. And now part B, the profit made by a company in its first 4 years of operation can be modelled by the function P, for which P of T equals the square root of T. And the profit is P times 10,000 after T years. So sketch the graph of the function over the time interval and calculate the average rate of change. So we've got our set of axes and our initial. So when t equals 0, we have the square root of 0, which is 0, and we have 4 years, so p of 4, square root of 4, which equals 2. And so we have our 2 points, one at 0, 0, the other one at 4, 2. So there's our spots. So we got 0, 0, and we'll go 4 and up 2. It's about there. So calculate the average rate of change of the profit over the first 4 years. If we have a look at the actual function p of t, it's a square root function, and if you remember back to first semester, square root function looks like that. So that's the actual function, that's our average rate of change over the time interval. So average rate of change for our profit is going to be P of 4, which is our final take initial, over 4 take 0, which is the time. So P of 4 was 2, take 0 over 4, so we have a half. So since the profit is P times 10,000, the profit of increasing at an average rate of 5,000 per year over this time interval. So we have 4 years, we calculate the average rate of change is a half. We have the profit is 10,000 after T years. We increase as an average rate of P times 1,000, so 1/2 times 10,000 equals our 5,000. So we increase at $5,000 per year. Instantaneous rate of change. So the gradient at any point on the graph of a function is given by the gradient of what's called the tangent to a curve at that point. So that gradient measures the instantaneous rate of change or rate of change of the function at that point or at that instant. So if we have the graph over here and we're interested as the rate of change at A at that particular point, we can draw a tangent to that point, which will give us the instantaneous rate of change at that point. So instead of calculating the average rate of change for the whole function, okay, it's normally it would be calculated like that. So final take initial, and that might be a gradient of 2, for example, whereas it's clearly that at A, the rate of change at that point is much more steep. So the rate of change is going to be greater at that particular point rather than looking at it across the whole interval. And if we have a look at point B, our gradient or instantaneous tangent at that point is decreasing, which is obviously the opposite of the average rate of change over the whole function. And same thing for C, it's very similar. So that's what we're talking about when we say instantaneous rate of function. Rate of change of the function is it's a particular tangent at that point, not over the whole interval. So at the turning point, the function is neither increasing nor decreasing. So if we have a look at that example again, if I have a look at point D there and draw a tangent, it should be pretty much horizontally, meaning the function is neither increasing nor decreasing. So we've got a horizontal tangent, meaning the gradient is 0. The rate of change of a function is measured by the gradient of the tangent to its curve, and for nonlinear functions, the rate of change is not constant and its value depends on the point or an instant which it is calculated. So there's a couple of different methods of calculating or estimating the gradient of a curve. And so we have method 1, draw the tangent line at P and obtain the coordinates of 2 points on this line in order to calculate its tangent, its gradient. The other option is calculate the average rate of change between the point P and another point on the curve which is close to P. So these are estimations, it's not exact at the moment. So just elaborating on those two parts there, we have a look at worked example 2. So for the curve y equals 5 take 2x squared, we want to estimate the gradient of the curve at the point 1, 3. So over here, 1, 3. Construct a tangent at P and calculating its gradient. Draw a line. So we want to construct a tangent at P. Now, that's way too thick. That's alright, I'll try and draw as straight as I can. So if we draw a tangent to that point, we get a straight line. And we want to calculate its gradient. So we know the point P is 1, 3. And we want to estimate a second point on that graph. And if we have a look, well, it's not really easy to see. So this is the first method. So we drew the tangent and we're obtaining the coordinates of 2 points on the line in order to calculate its gradient. So we've got 1 point, need another point on that red line, and this one up here is probably the best we can do, and it looks about 7. So if that's 5, it's about 7. So close enough. That's the best we can do. If you had graph paper, okay, you could draw the line on the graph paper and draw a tangent to that point. You might get a bit more accurate answers there. So we're just estimating at the moment. And we can calculate that gradient as 7 take 3 over 0 take, oh, hang on, other way around. That's point 2, point 1. So if we go 3 take 7 over 1 take 0, we get -4. So it's about -4. The second point, part B, choosing a point on the curve close to P and calculating the average rate of change between P and this point. So this is using the second method. So if we know that point P is 1, 3, a point that's close to P, we might choose as very close, which would be 0.9, or we can do 1.1, something like that. So our y coordinate at that point would be using our function. So 5 take 2 times x, which is 0.9 squared. Work that out and we get about 3.38. So that's our first point. It's a point that's close to P, and we can calculate the average rate of change as 0. So we want our final position, which was 3 take 3.33 over 1 take 0.9. So we should get about -3.8. So the gradient of the curve at the point P is approximately equal to -3.8. Okay, so that's it. So they're the two different methods of estimating the gradient of a curve. We'll have a look at other methods later on in the chapter, but at the moment these are the best we can do. Alright, thanks for watching. Have a go at the questions.